So you have followed, hopefully you have understood this concept, transformation of random variable, but note that all this theorem it will be applicable for the continuous random variable only, but for convolution case also it will be applicable, all these things. But what about the discrete case? Discrete case we cannot use this theorem. So because this derivative we cannot do approach. So discrete case, let us do one example. Directly we have to find what is the probability. This example we have earlier we have studied once. Let us for the context of transformation of random variable, let us discuss again. Let x and y are independent Poisson random variables with parameters lambda 1 and lambda 2 respectively. Find the probability mass function of z is equal to x plus y. So here you can see that because it is a discrete random variable, x and y are both discrete random variable, we cannot use this theorem here. So we have to use directly, we have to see without using the theorem, we have to check how to do that. Let x1 and x2 be Poisson, so they are independent Poisson random variables, independent Poisson random variables with parameters lambda 1 and lambda 2 respectively. Independent Poisson random variables with parameter lambda 1 and lambda 2 respectively. Find the probability mass function of z is equal to x1 plus x2. So how we can do that? We cannot use that theorem because it is a discrete random variable. Let us do directly. So how will be the range? So since x1 has Poisson distribution with parameter lambda 1, range of x1 will be 0, 1, 2 like this, and the probability mass function of x1 can be given by x1 is, so p of x1, this is probability that x1 is equal to x1. So it can be represented as e to the power of minus lambda 1 to the power x1 by x1 factorial. Whenever x1 is 0, 1, 2 like this is equal to 0 otherwise. Now similarly, and x2 is Poisson lambda 2, so range of x2 also will be same 0, 1, 2, and the probability mass function of x2 will be, x2 can be given by p of x2 This is probability that x2 can taking the value x2. This is similarly e to the power of minus lambda 2 to the power x2 by x2 factorial. x2 is 0, 1, 2 like this, and this is 0 otherwise. Now what will be the range of z? So z is x1 plus x2. So range of x2 is 0, 1, 2, range of x1. So range of z will be, first we have to understand, minimum values of x1, x2 can be 0, it can be 1, 2, any value. Range of z also 0, 1, 2. So how we can find the probability mass function of z? So the probability mass function of z, suppose then we have to find probability that z of z. So probability of z is equal to small z for this z belongs to in this range of z, this is nothing but 0, 1, 2 like this. Now let us do one by one. What is, suppose small z is equal to 0. So suppose pz of 0. So nothing but z is equal to 0. How we can find that? So this value will be, it is possible z is equal to x1 plus x2. This is equal to 0. Now how it can be possible that this sum will be 0? Because this range contains minimum value 0. So this is possible if x1 is 0, also x2 can be 0. This is only possible that x1 plus x2 will be 0. So because they are independent, so then we can write this is nothing but probability x1 is equal to 0 into probability x2 is equal to 0. Now this probability we can multiply and we can find that. So this is x1 is 0 e to the power of minus lambda 1, this is e to the power of minus lambda 1 and e to the power of minus lambda 2. So it is e to the power of minus lambda 1 plus lambda 2. Now let us find the next z is equal to, suppose next value 1. So let us find z is equal to 1. So this is probability that z is equal to 1. This is x1 plus x2 is equal to 1, which is nothing but, so how we can find x1 plus x2 is equal to 1? What is the possibilities? One possibility that x1 is 1, x2 is 0, and another possibility that mutually exclusive we can add the probability x1 is equal to 0 and x2 is equal to 1. This is the two possibilities. So because they are independent, so this is x1 is equal to 1 into probability of x2 is equal to 0 plus probability of x1 is equal to 0 into probability of x2 is equal to 1. Because they are independent, we can write that. Now what is probability of x1 is equal to 1? To the power of minus lambda 1, lambda 1 to the power 1, and this is e to the power minus lambda 2, lambda 2 to the power 0 by 0 factorial, plus it is the power minus lambda 1, lambda 1 to the power 0 by 0 factorial, and to the power of minus lambda 2, lambda 2 to the power 1 by 1 factorial. So finally what we got? This is e to the power of minus lambda 1 plus lambda 2 into lambda 1 plus e to the power of minus lambda 1 plus lambda 2 into lambda 2, which is e to the power of lambda 1 plus lambda 2 into lambda 1 plus lambda 2. So this is we found. So in general, for any z, so we get some pattern now. So then, so how we can find? For any z, suppose p of z now, we can in general we can write, you can check that. So this is nothing but probably that z will be some value z. So it may be 0, 1, 2, any value. So this is z, this is nothing but x1 plus x2 is equal to small z. Now how we can find that? So it will be summation of like this sum. So some r can be 0 to any value z such that probability that x1 will be some r and then x2 can be the remaining part z minus r. So then this is the, so you can check that for any other value 0, 1 or 2 any value it is actually coming. So basically if it is r is equal to 0, x1 is 0, then x2 has to be z. If r is equal to 1, then x1 is 1, then x2 will be z minus 1, then only sum will be z. So this is the general we can find out. Then summation r is equal to 0 to z, probability that x1 is equal to r, because they are independent we can write that x2 is equal to z minus r. So let us do in the next page. So p of z, what we found it, p of z, small z, this is probability that z is equal to z, this is equal to summation r is equal to 0 to z, probability that x1 is equal to r and probability that x2 is equal to z minus r, x1 is equal to r and x2 is equal to z minus r. So now we will use this probability mass function, this is r is equal to 0 to z, x1 is equal to, because of Poisson random variable lambda 1 parameter, so it is e to the power of minus lambda 1, lambda 2 1 to the power r by r factorial, and this is e to the power of minus lambda 2, lambda 2 to the power z minus r by z minus r factorial. Now we want to simplify this. So this is e to the power of minus lambda 1, e to the power of minus lambda 2. So e to the power of minus lambda 1 plus lambda 2, it is independent of r outside this range. Now summation of r is equal to 0 to z. So this is lambda 1 to the power r, lambda 2 to the power z minus r by r factorial, and this is z minus r factorial, and this is lambda to the power r, lambda to the power z minus r by r factorial, z minus r factorial. Now how we can simplify this? So let us multiply one r factorial here, no z factorial here, because it is z factorial here, and this is independent one constant here, I just divide by outside z factorial, then this is cancelled. Now how then what is this value? So you can know that this binomial expansion. So suppose if you want a plus b whole to the power some n, so this can be represented as r 0 to n, then n factorial r, then r factorial n minus r factorial, a to the power r and b to the power of n minus r. So then this is a plus b whole to the power n. So here you compare with this, then you can see that if you compare with n is equal to z here, and then r is this is r factorial n minus r factorial, yes. So z minus r factorial, a to the power r, lambda 1 to the power r and lambda 2 to the power z minus r. So this is nothing but this is e to the power of minus lambda 1 plus lambda 2 by into this is nothing but lambda 1 plus lambda 2 whole to the power of z by using this binomial expansion by z factorial. So this is for any values of true, for any values of 0, 1, 2 like this, and for any other values it is actually 0. So we can write Pz of z is equal to finally e to the power of minus lambda 1 plus lambda 2, lambda 1 plus lambda 2 whole to the power of z by z factorial whenever z is 0, 1, 2, this is 0 otherwise. So this is also, this distribution also very similar looking with the Poisson distribution, which implies that z also Poisson distribution with parameter lambda 1 plus lambda 2. But this method also we can find the transform probability distribution function we can identify, but this is little complicated. So we did this example earlier also, but to in the transformation of random variable context we just wanted to explain again. So to show that this is very time consuming and complicated, so we want some if there is any simplified technique. So now suppose next if you ask this, so let suppose y1 y2 yn be independent Poisson random variable with parameters lambda 1, lambda 2, lambda n respectively. So find the probability mass function of z is equal to y1 plus y2 plus yn. So then it is we can find in the previous approach, but because we did only y1 plus y2, we can do for y1 plus y2 plus yn. So it may be, it will be true that this will be a Poisson random variable by adding the parameter, but for showing it, it will be very complicated. So that's why we will show some other technique. So we need some other technique actually. So we'll discuss some other method, or whether there is any kind of some simplified approach that we can find the distribution easily instead of going through all these details. So in the next we'll discuss some other topic. It is known as moment genetic function that may be useful for finding the distribution of such kind of transform random variables.